Okay. Forced oscillations. So damping may exist for forced oscillations, or it may not. It can vary. The general gist behind forced oscillations are you have another situation. It can be a mass on a spring, it can be a pendulum, it could be anything that leads to a harmonic oscillator type situation. In this case, we'll think about it as being inside a material that gives it a constant of damping. And then we're going to connect up to some kind of forcing device. So maybe as this rotates around, it causes a force that pushes the mass back and forth. So that forcing function will have some force F naught, and then we'll drive it something like sine of omega t. Hold on, need to think about that for a moment. Sine of omega t or sine of omega naught. Yeah, I do want the omega. That will be consistent with the textbook. An example of something that would work like this would actually be kind of pushing someone who's on a swing, for instance, or even being on a swing and kind of doing the rock back and forth motion that makes the swing move. So that would be a forced oscillation. Alright, so if we think about the forces that are acting on the mass, we're of course going to have our forcing function acting on it. We'll have our minus kx, and in one direction or another we'll have our minus bv. So it's pretty similar as far as the setup goes. So we might have f minus kx minus bv equals ma, and when we rearrange it, this one's going to look a little bit different. The forcing function can't be moved to the other side. It doesn't depend on the same quantities. So divide through by m. And we'll go ahead and plug in for our forcing function, and we get something like this. Now, I'm sure you notice that this looks a lot like the damped harmonic oscillator, and it is. It is a relative of it, but it's not the homogeneous case anymore. It's not the equals zero case. The solutions get a lot more interesting. It's harder to work out. And I'm not going to go through the effort here. It's definitely beyond the scope of this class. When you take your differential equations class, they may get into this. But you'll find that the position x will look like a cosine of omega t, probably with a phase. But the amplitude is not simple. It will actually look like f naught over m, and then on the bottom there will be an enormous square root, where you'll have omega squared minus omega naught squared. You're probably thinking, wait, what's omega naught? We'll talk about that next. Omega naught is what you would call the natural frequency. Technically, it would be the natural angular frequency. As an example, if you were looking at something like a mass on a spring, omega naught for a case like this would look something like k over m minus b over 2m squared. So the natural frequency would be whatever frequency the object would oscillate at if you gave it a push and then stopped and you didn't try and force it. You just let it oscillate on its own. So for instance, in a swing, it would be whatever frequency the swing would oscillate at if you just gave it a little bit of a push and then let it swing back and forth on its own. Or a mass on a spring, you push it a little bit to the side and let it just naturally oscillate on its own. Okay, there are some interesting things to notice about this. And the first one is you can actually get this first term to go away. If omega naught squared is equal to omega squared, that term disappears, and then the amplitude will only depend on the forcing function and the damping that's present. Okay, if there's no damping, that means it's actually possible to divide by 0. And hopefully that thought strikes terror into your hearts. So what does that mean for us? Well, it means if you look at the amplitude versus the frequency, and we plot a mega naught somewhere here, if we're looking at b is equal to 0, you're going to get a weird point there. The system will attempt to have an infinite response. It will try and have an infinitely large amplitude. The amplitude will increase without limit as you approach a mega naught. Now, fortunately, things are a bit more well behaved as we go to other values. If you make b small, you'll get a bit of a shorter peak. It will never actually try to go to infinity, and if you make the damping large, it will actually stop at a more reasonable value and not try and go to infinity at all. Now, you're actually familiar with this effect. Drive at natural frequencies to break stuff. So, wine glass with voice. That's an example. You sing the right note, ah, and you can shatter the glass. There's a Mythbusters episode on that one where they have a guy doing it without amplification. Worth a look. We'll actually talk about this idea again later. There's also a very famous example of shake a bridge apart. My dad's first job when he finished his degree, he did double E electrical engineering. He got a job at Hughes Aircraft, worked on a thing related to the shake table. So they'd take the electronics, they'd put it on the shake table, they'd shake it at a variety of frequencies, and he'd talks about how, they'd finish the shake test, and sometimes he'd just sweep the parts into the box and take them back to the engineering office and be like, well, here you go. If you drive things at their natural frequencies, you can shake them to pieces because they have a strong response to that frequency. And if the damping isn't low enough, they come apart. This is one of the reasons you sometimes see electronics intended for cars or airplanes. They'll have this weird celastic stuff, kind of a glue that's all over the parts. And it's to try and hold them together, essentially increase the damping so they can't shake themselves off the board. Okay, we do have a practice problem on this. That will be the next video, and that is it for forced oscillation, and technically the end of the material in this chapter. So look forward to coming up next, chapter on, oh gosh, it's going to be traveling waves.